All right, now I'd like to provide some examples on different kinds of problems that we encountered. Now, a lot of these, some steps are omitted. I'm showing you the problems, I'm showing you the solution, and I'm going to step through with you how to get from the problem to the solution. I should point out that if you've come to class, we've worked numerous examples in great detail, so I'm not going to go into that kind of detail in this review, but I will refer you back to the notes to some previous examples that we've done. So the first thing I want to look at is going back to step functions. How do we use step functions to provide expressions for functions like the one shown in the figure? So this is a function that clearly, if we were not going to use step functions, we'd have to define the fact that it's 0 for t less than -5. It has the following equation of the line for t between -5 and 0. And then there's a discontinuity, and we would have a different functional expression for this straight line from 0 to 5. And then the function again is 0 for t greater than 5. So this is what we would refer to as a piecewise linear type of function. Now, using step functions enables us to write this all as a single expression. So you would divide it into its four parts, and then realizing that for t less than -5 and t greater than 5, the function is 0, all we really need to do is ensure that we don't have any step function activity for t less than -5, and that everything sums to 0 for t greater than 5. So the first thing that we do is we create a window from -5 to 0. So that's this part of the expression right here. This u of t plus 5 minus u of t, that basically turns on a step function at -5, and it turns it off, turns it on at -5, and it turns it off at 0. Now then, that step function is going to multiply the equation of this line. If we just write the equation of the line, it'll extend from -infinity to infinity in the time domain. So we don't want that. We want it windowed with the step function. So as long as we multiply the equation of the line times the step function window, then we're okay, and we've represented just this segment. So the equation for this line, it has a slope of -3 and it has a y-intercept of -15. So the slope is -3t minus 15. So we take the equation of that line segment and we multiply it by this window. The next window will occur from t equals 0 to t equals 5. It will multiply this line. So the equation of this line is -3t plus 15. The slope is -3. The y-intercept is 15. And then we have this window that turns that function on at t equals 0 and turns it off at t equals 5. Now, this second line is just simply a collection of like terms. So we can factor out the 3. We can make this t plus 5. And then we can distribute it across each term. And then we can do the same for the second series of terms. Collecting like terms in the step function, we find that we have one that's shifted t plus 5. We have one that's not shifted at all. And we have one that's shifted t minus 5. So this is just another way to write this expression, and if you're thinking about Laplace transforms, you can see that this would be easy because the time shift is the same everywhere. Now let me add an important statement about the Laplace transform. If we were to take the Laplace transform of this expression, so if I were to ask you to find the transform of this function, the first term is a portion of the function that exists prior to t equals 0. So in taking the Laplace transform, we would ignore this first term. It's like it doesn't exist. So the Laplace transform would only occur on the second and the third terms where the Laplace transform, the single-sided transform, is defined. The next example is an example of how to use integration with impulse functions. So here are just a couple of examples of some impulse functions within an integral, and then shown below is the solution. So if we look at part A, basically what's in the square brackets here is distributed into two separate terms with the integration limits remaining the same. So we have that first impulse function in this term, and then we have the second shifted impulse in this second term, And then remember the property, the shifting property of the impulse function is we take its location, which in this first term is 0, and we substitute that everywhere in the function under the integral sign. So we would substitute 0 for t, and we keep our 2. In the second term, this shift occurs at 1, and so we take 1 and we plug it into t cubed, so we'll get 8 times 1 cubed plus 3. So basically the answer is given here as 26. Same kind of thing on this second expression. We basically have t squared times 3 different impulse functions, each with different shifts. We split that up into 3 different integrals. The thing that is unique here, notice the integral limits go from -2 to 2. So the first impulse function occurs at 0, we can apply the property. The second impulse function occurs at -1.5, which does lie within our integration limits, so we can apply the property as shown here. The third part of the integral, the impulse function occurs at t equals 3. That lies outside of the range of integration limits. So by definition, because that's outside of our integral, this is basically equal to 0 everywhere inside the integral. So we replace that with 0. So the answer then is 2.25. Here are some examples of Laplace transforms. The first one is just an exponential with a time shift, and notice it's multiplied by a step function that also has a time shift. When we take the Laplace transform of that, we would take the Laplace transform of the exponential without the time shift, which would be the constant 20 over s plus 500, and then the time shift basically introduces this e to the minus 10s term. So this is a property both of looking at the table as well as applying the time shift property. In the second expression, we have a series of step functions. I won't go through each individual step. What the textbook author has done here is first he has taken this expression and he has multiplied this out term by term. Then he combines some like terms, and fortunately in this particular example, when you combine like terms, it turns out that you can put this algebraically in an expression where each functional form of t corresponds to the time shift. So notice how this is organized. You have 5 times t plus 4, and then you have u of t plus 4, and so on. So each one of these terms then corresponds to a given time shift. Now, I want to point out that there is actually an error in the textbook answer, because theoretically in these first 2 terms, because time exists before t equals 0, you can't really take a Laplace transform of that term, because our Laplace transform definition is defined as existing only for t greater than or equal to 0. So there is a mistake here. These first 2 terms technically should not be here. You technically should only have these last 2 terms. So that's a key illustration of A, the fact that textbook solution manuals aren't perfect, but B, the fact that you can't have negative time when you're taking a Laplace transform. It's fine. The time domain expression is fine. It's perfectly legitimate to have this function and to have this time domain expression. It's just that when you take its transform, and notice here when attempting to do that in the solutions manual, you get these positive exponentials. Now, s is not the time domain, but still typically you don't want a positive exponential, because remember s represents sigma plus j omega, and so you have some odd positive exponential in your Laplace domain, which is not physical. So these first 2 terms, they don't exist. Okay, here are some additional, here are some inverse transform examples. Now, once again, I did numerous examples in class on how to take the inverse transform using partial fraction expansions. So I'm going to refer you back to those notes rather than go through a detailed discussion of each one of these. But what I want to accomplish out of this review is to point out that for different kinds of functions, we know already what the time domain solution is going to be here. So if you look at part C, you see that this has three real negative roots. So as we go through the process of doing the partial fraction expansion and finding the solution, I already know that in the time domain, this solution is going to look like the sum of three exponentially decaying terms. Likewise, if I look at D, first I want to do my little check. I notice that my denominator is of lower order, or my denominator is of higher order than my numerator. So partial fraction expansion will work on this problem. I notice that I have three real roots, and they're negative. So I have a root at -1. And then if I were to factor this, I would get a root at -2 and a root at -3. And then I notice I have a pole at 0. So this is a root at s equals 0. So I know that if I have a 1 over s term, that transforms or inverse transforms into a step. So this expression, because I have this s in the denominator, will be a step function plus the sum of three exponentially decaying terms because I have three different negative real roots in the denominator. So we'll go to the next slide for the solution. So your textbook author uses a slightly different form to express the solutions for the partial fraction expansion. So what I've done here is I've added in a step. So if we were to take our original function, which is shown on the previous slide, and multiply out by the denominator, we would obtain the following expression. So what the textbook author does is he says, all right, if I want to solve for k1, I want to do that where s is equal to -2 so that k2 and k3 will go to 0. And so then what he does is he takes and divides through by the s plus 4s plus 6, and that gives an expression for k1 alone when evaluated at s is equal to -2. So then you would plug a -2 in here for s. That would give you the expression for k1. So he really hasn't done anything different from what we did in class. He just expressed it in a different way. So after all of that, you'll get 8, -5, and 12 for k1, k2, and k3 respectively. When we take the inverse transform of that term by term, we do indeed get three exponentially decaying terms, and then of course, because this is Laplace, those are all turned on at t equals 0. So we have the multiplication by the step function. That's a little bit different from this case, where we have this term, this 1 over s term. So once again, going through all of the partial fraction expansion, you can get expressions for k1 through k3. Sorry, k4. This should be k4. Another mistake in the textbook solutions manuals. This is why we don't distribute those. So now, if you inverse transform each term, you find that this first term, this 9 over s term, basically is going to inverse transform into 9 times u of t. So that's our step, and then here are our three exponentially decaying terms. Okay, here are some more examples of slightly more complicated functions. So once again, what I want to do is I want to look at the denominators before we find the inverse transform of these. I want to look at the denominators and I want to determine what would the functional form in the time domain be. So in this first one, because we have this s squared term, the partial fraction expansion will contain a k over s term, a k over s squared term, and a k over s plus 8 term. So that's going to inverse transform into a step, a ramp, and a decaying exponential. In this term, we will have something times 1 over s, something times 1 over s plus 2, and something times 1 over s plus 2 squared when we do our partial fraction expansion. So that will inverse transform to look like the sum of a step, a decaying exponential that comes from the s plus 2, and a decaying exponential times a ramp that comes from the s plus 2 squared. In part C, we have this s plus 1 squared term again. So that one will produce basically the decaying exponential and the decaying exponential times a ramp. And then we have this other term that if you look at it, it does not factor into real roots. It actually factors into complex roots. So anytime we have a term in the denominator that has complex poles, basically the time domain result of that will be an exponentially decaying sinusoid. Depending on the approach you use in your partial fraction expansion, whether you complete the square or whether you use MATLAB or factor into complex poles, you will either get a time-shifted cosine, so a cosine with a phase angle, or you will get one term that is an exponentially damped sine and one that's an exponentially damped cosine. So it just depends on whether you do this through completing the square or whether you do it through factoring into complex roots. Once again, I'll refer you to the numerous examples we did in class where we completed the square in order to obtain the solution to this. The solution that's going to be given here is going to be given in terms of complex roots. And then finally, for the last example, you see we have a second order pole at 0. That's going to give us a step and a ramp. And then we have a second order pole at -5. That's going to give us an exponentially decaying function and an exponential decay times a ramp. So the reason I'm going through this is that a lot of these kinds of problems are too extensive and time consuming for you to complete in the course of a single 1.5 hour exam. So what I want you to know is that I may very well pose a question like this that asks you to look at a function and rather than taking the inverse transform, predict for me what kinds of terms will be in the solution. So that's a kind of question that I often, on these more complicated, like Part C, that's a pretty lengthy and complicated problem to work out. So I might either ask you to work it part way, or I might ask you what the functional form would look like in the time domain. So this is an example of how you would make those kinds of statements correctly. All right, here's the solution to part A. You can see, so what I want to remind you of is that you do have to, when you have that second order pole, you have to write one partial fraction term for the second order, one for the first order. So working through this, and you may use whatever method you choose. We introduced two methods. One was just substitution of different values of S. The other method that we introduced was equating different order polynomial terms. When you get down to the end, you can take the inverse transform term by term, and here is the expression we get, which is exactly what we stated on the previous slide, talking about the form that we might expect to see. So here is your ramp, here is your step, here is your exponentially decaying step. So here is the example from the second term. So you have a root at 0, then you had a second order root at 2. So we take the s plus 2 squared, we take the s plus 2. After doing the partial fraction expansion, and once again your textbook uses a slightly different method from what we used in class, but after taking the partial fraction expansion you can get K1, K2, and K3. And you can of course also do that using MATLAB. Then when you take the inverse transform of each term, the 1 over s term gives you the step, the K2 over s plus 2 squared term gives you the ramp times the exponential decay, and the K3 over s plus 2 gives you the exponential decay. All of that then is multiplied by the step function just to make us aware that this turns on at t equals 0. Here is the expansion done as your textbook does it, where we factored this into complex conjugate pair roots. The numerator would be K3 and K3 star. The first term, we have the second order term represented in the first term of the partial fraction expansion, and then we have the first order term in the second term of the partial fraction expansion. Each one of these is taken term by term. We get a value for K1, a value for K2, and then K3. And once again, so this is a problem that I would not give you this problem in its entirety. on a 1.5 hour exam because it's quite a lengthy problem. But what I would like for you to be able to know and understand is that this first term is going to generate this exponentially decaying ramp. The second term generates a simple exponential decay. And the third term, or pair of terms, whether it's written like this or whether you complete the square and write it as a problem with a completed square in the denominator, it's going to generate this exponentially damped sinusoid. If it's written like this, it'll be a cosine function with a phase shift. If instead you choose to complete the square, you'll have one constant times an exponentially damped sine and one constant times an exponentially damped cosine in general, keeping in mind that any of these constants could be zero, and that's a perfectly acceptable solution. So you have to generate each term in the partial fraction expansion, but you also keep in mind that those terms could be zero. And then here's a final example where we had the second order pole at 0 and the second order pole at -5. Here is our ramp, here is our step, here's our exponentially decaying ramp times a ramp, and here's our exponential decay function. So those are some examples of taking the inverse transform, uh, examples of different possible things that you might see there.